I'm Jeff Groh, and this is Partial Differential Equations. Today, we're going to begin with a discussion of Laplace's equation in rectangular coordinates in 2 dimensions. The Laplacian is the divergence of the gradient of some scalar valued function. The gradient of a scalar field is the vector valued function consisting of the partial derivatives, with the number of coordinates depending upon how many independent variables the dependent variable phi has. The divergence of a vector field f, let's suppose that f has coordinates m, n, and p, is the sum of the partial derivatives in this fashion. In other words, it's del dot f, where del is the vector of partial derivatives. So if you dot this vector with this vector, it's like taking the derivatives dx, dy, dz, dotting that with m and p, yielding the expression above. The Laplacian then is the divergence of the gradient of phi, which is sometimes expressed as nabla squared phi, and very commonly expressed as a delta phi. In rectangular coordinates, that's going to be the second order derivative of phi with respect to x, plus the second order derivative of phi with respect to y, plus the second order derivative of phi with respect to z. The sum of the second order partial derivatives of phi in each of the coordinate directions. Laplace's equation is then just Laplacian equal to 0. The Dirichlet problem is the Laplace's equation together with phi being defined on the boundary of whatever your region is defining this, is some function defined on the boundary. We're going to start by looking at the following Dirichlet problem. We'll have Laplace's equation, and we're going to define our region R as follows. We're going to go from 0 to A and 0 to B. 0 to A on the X, 0 to B on the Y. U evaluated on this part of the boundary, we'll call this boundary 1, boundary 2, boundary 3, boundary 4. U evaluated on boundary 2 will be identically 0. U evaluated on boundary 1 will be identically 0. U evaluated on boundary 4 is identically 0. However, U evaluated on boundary 3 is going to be some function of x. In other words, the function is going to be 0 at each of the 3 boundaries here, but when y is equal to b, then we get this function u bar. We're going to proceed by assuming separability. so that u takes the form big X, which is a function of little x, times big Y, which is a function of little y. If that's the case, then the differential equation gives us x prime prime y plus x y prime prime if we divide then both sides by xy. Then you can see that the y's go away here, the x's go away here. We'll have x prime prime over x, y prime prime over y. Now, how do we separate this? We'll move the y's to one side, and then we'll have the variables completely separated. All the x's on one side, all of the y's on the other. Writing this as x prime prime over x equals minus y prime prime over y, note, we might set this equal to minus mu squared. However, that does give us x is c1 cosine mu x plus c2 sine mu x. But for y, what do we do? What are the solutions where y prime prime is mu squared y? Well, you can choose either y equals c1 e to the mu y plus c2, we should use d's here, e to the minus mu y. We'll have problems with the initial data here since both of these basis functions evaluated at 0 are non-zero. So we might end up with some trouble. It might be easier if instead we used hyperbolic cosine and hyperbolic sine. After all, cosh and sinh are simple linear combinations of these two. So we're going to use d1 hyperbolic cosine of mu y plus d2 hyperbolic sine of mu y. Much more satisfactory since, after all, the hyperbolic sine of 0 is 0. Keep in mind that the function is 0 on 3 of our boundaries. X equals 0, x equals a will give us zeros, and y equals 0, but not necessarily y equals b. That's where the function might take on the values of this u bar that we've assigned. That tells us then that x of 0 is 0, but when we apply x equals 0, we'll end up with c1. So in other words, this term is out. Y of 0 must also be 0. Well, sinh of 0 is 0, and cosh of 0 is 1. So that gives us d1 is 0, and this term is out. But there's more. X evaluated at a must be 0, but x evaluated at a is c2 sine of mu a, and that implies that mu a is n pi, where n is an element of the set of natural numbers. Consequently, mu is n pi divided by a, and that's going to go both into the sine and into the hyperbolic sine. It follows then that u is the sum on n of an, the sine of n pi over a times x times the hyperbolic sine of n pi over a y. When y is equal to b, we'll have to satisfy the boundary data. Then, Remember that if we take the inner product of the sine of n pi over a x with the sine of n pi over m pi over a x, we get a over 2 if m equals n and 0 otherwise. From this, we deduce that an is 2 over a times the integral from 0 to a of u bar of x times the sine of n pi over ax, all over the hyperbolic sine of pi n over a times b. This gives us a complete solution to the problem. For a quick example, let's suppose that the boundary data is a constant. Then the coefficients a sub n in our solution are 2 u bar over a, integral from 0 to a, of, and we have the hyperbolic sine of pi n b over a, and then the sine of n pi over a x dx. Integrating, we have 2u bar over a hyperbolic sine pi n b over a. We'll have to divide by n pi over a. That puts an a and an n pi here. We'll get a negative cosine n pi over ax evaluated from 0 to a. When we plug in a, we'll just have cosine of n pi, which is negative 1 to the n. And when we plug in 0, we'll have 1. We can reverse the order of the subtraction and eliminate the minus. The a's go away. We'll have 2u bar over n pi hyperbolic sine n pi b over a times 1 minus negative 1 to the n. This gives our solution then to be the sum on n of this constant, 2u bar over n pi hyperbolic sine n pi b over a times 1 minus negative 1 to the n times the sine of n pi over ax hyperbolic sine n pi over a y. What do we do in the case where more than one piece of the boundary of the rectangle is non-zero? It's simple. The Laplacian u equal to 0 is linear. And that means linear combinations of solutions will be solutions. So if we have a u bar 1 as a function of x, u bar 2 as a function of y, u bar 3 is a function of x, and u bar 4 is a function of y, what we can do is we can find solutions u1, u2, u3, and u4 where the function is 0 except on the one side. So u1 is 0 except on the lower side here where it's u bar 1, 0 everywhere else. u2 is 0 everywhere except on the right hand side where it takes on u bar 2, and so on. U then will be just the linear sum of these solutions. We next turn to Poisson's equation. Poisson's equation, at least in 2 dimensions, we'll say equals f of x comma y, could be more variables or less depending upon the function u. Notice that this solves a steady state heat equation where you have an external source. But we're assuming here that ut is 0, and that implies a steady state. One of the most important factors to note is that this is very similar to the Laplace's equation, except it is non-homogeneous. Just as you learned in ordinary differential equations, to solve a non-homogeneous problem, you first solve the homogeneous problem, where you set it equal to 0. You have to first solve Laplace's equation, which we just did. So first solve Laplace's equation using whatever boundary data you need, and then add to that a particular solution that satisfies boundary data all 0. That way, when you sum the homogeneous and the particular solution, this will have all of your non-zero boundary data. This one will have boundary data all 0, and you'll satisfy the boundary data. Since the particular solution evaluated at the boundary is identically 0, we suppose then that the particular solution may be expressible in the following form. It's maybe the sine of n pi divided by ax sine of m pi divided by b y. In this case, we need 0 values at both 0, x equals 0 and x equals a, hence the sign here. And we need 0 at y equals 0 and y equals b. And hence we have the sine function here, not the hyperbolic sign. To get a solution, we first calculate the Laplacian of this proposed particular solution. Notice this is actually the sum of different terms second order derivatives with respect to x and y. That's going to give us the sum on both n and m of minus a n m. We'll get 2 factors of n pi over a, and then on a separate term 2 factors of m pi over b. That's all times 2 derivatives of sine gives you negative sine. We'll get by the chain rule these 2 factors. Using these as our Fourier basis, if this is equal to f, we take the inner product with these on both sides, and you'll see that we'll get a n m is minus this over times the double integral. We'll have f times the Fourier basis elements dy dx, where we've multiplied by 4 over ab in order to normalize. As a quick example, we'll look at the Poisson equation where the right-hand side is identically 1. U all the way across the boundary of our rectangle will be identically 0. This latter part gives us that the homogeneous solution is identically 0, and we only need to solve for the particular solution, and plugging in f equals 1 will give us the answer. With f identically 1, you can see that a n m will be this negative 4 over ab n pi over a quantity squared plus m pi over b quantity squared. And then when we integrate this part here, the integral of the first part will be negative 1 to the n minus 1 divided by n pi a. And on the second part, we'll have b times negative 1 to the m minus 1 over m pi with the b on the top. The ab's go away. We can take a pi squared out of each of these terms, get another pi squared. We'll end up with pi to the fourth in m all times this expression. And plugging these into the formula for the solution, the problem is solved. In particular, u will be the sum on both n and m. We'll have negative 4, negative 1 to the n minus 1, negative 1 to the m minus 1. We had pi to the fourth nm times n over a squared plus m over b squared times the sine of n pi over ax sine of m pi over b y. So we've solved the Laplace equation and the Poisson equations on the rectangle. We're next going to turn our attention to the Helmholtz equation. In the Helmholtz equation, we again have the Laplacian, but it's going to be minus lambda u on the right-hand side. To begin with, we'll assume that u evaluated on the boundary of our rectangle will be identically 0. This is akin to something we call an eigenvalue problem. Let's review the concept of eigenvalues and eigenvectors from linear algebra. A function L, which maps one vector space into another, is called a linear transformation if the following is true: L of u plus CV equals L of u plus CL of v for any u and v in the domain, and C, which is an element of the field in question. We will take the field, blackboard bold F, to be a member of the set of real numbers or the set of complex numbers. A linear transformation is called a linear operator if L maps a vector space into itself, if the codomain is the same as the domain. Then the linear transformation is a linear operator. Let me give you an example. The derivative operator maps infinitely differentiable functions into infinitely differentiable functions. For instance, it takes e to the x and outputs e to the x. Well, taking one derivative didn't reduce the total number of derivatives on something that's already infinitely differentiable. And so it's mapping the set of infinitely differentiable functions into the set of infinitely differentiable functions. That these are vector spaces results immediately from the definition of vector space. And this is a linear operator between these vector spaces. Let L be a linear operator we say that lambda is an eigenvalue of L with corresponding eigenvector v if L of v is just a scalar multiple of v, lambda v. So these eigenvectors are special because the linear transformation maps them into something that is just a rescaling of that same direction in the domain space. As an example, take a look at the derivative operator, which maps C infinity into C infinity. The derivative of e to the ax is a e to the ax, which means that a is an eigenvalue for any a in the set of complex numbers. And also e to the ax is an eigenvector for the derivative operator. Now, for the Helmholtz equation, there was a very conspicuous minus sign, which means that minus lambda are going to be eigenvalues, and u will be the eigenvectors, whatever u's satisfy this equation. It's our job to figure out the lambdas and the u's. Now, you might be wondering why we would opt to use a minus here. That will become apparent in a few moments. We're going to first look at the one-dimensional case, where we're going to assume u at 0 is the same as u at a, and that is going to be 0. So at the endpoints of some interval, the function takes on values that are 0 at each endpoint. Because of the boundary data, it makes sense to try u's of the form sine n pi over ax. Note then that the second order derivative will be minus. We'll have two factors of n pi over a by the chain rule times the sine of n pi over ax. You can see then that the second order derivative is a scalar multiple times the original function with a minus here. Minus lambda, which I'll put as a little subscript n then, will be minus n pi over a squared. So our lambda n's will be n pi over a squared. And now maybe you can see why we wanted to put this negative onto the differential equation to account for these second derivatives giving us a negative in this case. We have then a discrete class of eigenvalues and eigenvectors that all solve this differential equation together with the boundary conditions. We have then a class of solutions and eigenvalues. The eigenvalues are the negatives of these lambda n's. Notice that linear combinations of these don't give you solutions because they have different constants lambda n for each of these functions. Also, you don't get solutions for arbitrary lambdas, only for specific lambdas that we've discovered so far. We're next going to turn to the 2D Helmholtz problem. We're going to assume u at the boundary of a rectangle is identically 0. The rectangle is defined by 0 to a and 0 to b. And it makes sense to try solutions of the form sine n pi over ax sine m pi over b y. It's not hard to see that in this case, the eigenvalues associated with these eigenvectors will be of the form n pi over a squared plus m pi over b squared. Yes, when you take these second order derivatives, you'll get a minus and then two factors in two separate terms because we add the second order partials together. That gives us lambda nm having this exact form. We're now going to look at kind of a hybrid problem on the unit square where u evaluated on the boundary of the unit square is 0. Because u is 0 at the boundary, it makes sense to try u of the form the sum m and n of a m n, the sine of n pi x, the sine of m pi x. Notice then that the Laplacian is going to be the same sum with a minus mn times the factor n pi squared plus m pi squared. This should be y. And we want that to be equal to the expression on the right-hand side. On the right-hand side, we're going to have a times this sum of the a m n's, the sine of the n's, the sine of the m's, plus b. We'll move this term to the other side to join these and then have the whole thing equal to the constant function b. At that point, we'll try to use our Fourier analysis to separate and figure out the values for a m n. When this term comes over to join these, it will get a negative. We'll factor the negative out. We'll have negative, the sum on the m's and the n's. We'll have an a added on. a m n will come out of everything. And then we'll have the sine of n pi x times the sine of m pi y, and all of that will equal b. Taking the inner product on each side with the sine n pi x sine m pi y, we'll get a m n is minus, we'll get a 4 over 1 times 1. We'll have to divide. Let's call this lambda mn. We'll have lambda mn plus a down here. The integral from 0 to a, the integral from 0 to b of b times these sines. That gives us negative 4 over the lambda mn plus a. We'll have this b coming out. We'll have an n pi and an m pi in the denominator. Two negatives from the integrals gives you a positive. We'll have pi squared mn. And then when we take the integrals here, negative 1 to the n minus 1, negative 1 to the m minus 1. Plugging these back in for a m n in our formulation for u gives us a solution to the problem. We're going to give an alternative solution to the Poisson equation. It illustrates a lot of nice analysis. As you'll recall, the Poisson equation is of this form, and we are specifically going to assume that when we evaluate on the boundary of our region the solution, that we get 0. We're going to try a solution of the form u, which is the sum on n, as n goes from 1 to infinity, of some a n of y times the sine of n pi over a x for some functions a n of y. If we apply the Laplacian to u, we'll have the sum on n, we'll have two derivatives when we take the derivative with respect to y on the function a n. And when we take the derivative with respect to x, we'll have minus n pi over a quantity squared times a n of y, and both terms will have a factor of the sine of n pi over a x. Since the Laplacian of u is equal to f, f we'll assume can be expressed in the form the sum on n of b n of y sine n pi over a x. Taking the inner product on both sides of this equation with respect to our basis function sine of n pi over a x, we'll have b n of y is 2 over a. The integral from 0 to a of f of x comma y times the sine of n pi over a x dx. So we have everything over here equal to everything over here. Equating coefficients on each side, we'll have a n prime prime of y minus n pi over a quantity squared a n of y equals these b n of y's. This is a second order differential equation that you studied a lot of in ordinary differential equations. It's non-homogeneous, which means you need to use some method for solving non-homogeneous equations. One of those methods that you studied in ordinary differential equations was called variation of parameters. So first, a little review of variation of parameters. It applies to differential equations, say, of this form, y double prime plus by prime plus cy equals some function of x. Let's suppose the derivatives here are with respect to x. The idea is that if y1 and y2 solve the corresponding homogeneous equation, we'll set y equal to v1y1 plus v2y2. We know that any linear combination of these homogeneous solutions will also be a homogeneous solution. But there, we require constants c1 and c2. By making these functions, we're varying the parameters c1 and c2, and allowing them to be functions instead. The formula for solving for v1 and v2 are as follows. v1 is minus the integral of y2f over the Wronskian. Here, the Wronskian is the determinant of the matrix y1, y2, y1 prime, y2 prime. And v2 is the positive integral of y1f over the Wronskian dx. This shows you how to construct these functions v1 and v2 to within some constants, but those constants will only contribute to homogeneous solutions, so you may ignore them. So let's apply this method in solving the differential equation that we derived when trying to solve the Poisson equation. Remember, the differential equation was a n pi prime of y minus pi n over a quantity squared a n of y equals b n of y. The first step is to solve the corresponding homogeneous equation. And that's going to be a n prime prime of y minus this constant, a positive constant, pi n over a quantity squared, a(n of y equals 0. It's easy to see that two solutions might be y1 equals e to the pi n over a y, and y2 equals e to the minus pi n over a y. This is one basis for the solution space. But we can make linear combinations of these and find other solutions. Let's call this basis 1. Another good linear combination of these that we could try would be y1 equals the hyperbolic cosine. After all, the hyperbolic cosine is just the average of these two, y1 plus y2 over 2. Remember, it's the hyperbolic cosine of x is e to the x plus e to the minus x all over 2. So this will be the hyperbolic cosine of pi n over a all times y. Similarly, y2 will be the hyperbolic sine pi n over a times y. And this will provide a second basis by which we can construct solutions. It turns out both of these bases are problematic. But there's a unique trick that we can use to construct something that will work. Let me show you why these are problematic. We need for our functions to be 0 at y equals 0. For b1, we require y1 of 0 to be the same as y2 of 0 to be 0, but they're both 1, not 0. So we'll never meet the boundary condition. For basis 2, we at least get y2 of 0 is 0 because the hyperbolic sign passes through the origin. But you don't get y1 to be 0. You might still hope that your v1 of 0 equals 0, and you can check, but we still require that both of these at b is 0, but that's not going to happen. Not with this one anyway. So we're kind of at an impasse. A way forward might be suggested by the fact that certain translations of the trig functions are linearly independent. Let me give you an example. Suppose we have sine of x for our first basis function and the sine of x plus 1 as our second basis function. Let's calculate the Wronskian. Well, we'll have sine of x plus 1, cosine of x plus 1, which gives us sine of x cosine x plus 1 minus cosine of x sine of x plus 1. At this point, we use the difference of angle identity for sine to get the sine of minus 1, which is the negative sine of 1. And sine is only 0 at integer multiples of pi. So this is certainly not 0, which means these two functions are linearly independent. Might we do something similar down here that allows us to satisfy our boundary conditions? That's the trick. We're going to try a third basis that consists of the hyperbolic sine pi n over a b minus y, and then the hyperbolic sine of pi n over a y as our new basis. To solve our differential equation, the ordinary differential equation, we need to use variation of parameters, and that is going to require us to actually calculate the Wronskian. So that's going to be the determinant of the sinh of, I'm going to use a subscript b minus y, and here we're going to have a sinh of y, and when we take the derivative, we're going to get a minus pi n over a cosh, I'll say b minus y, and over here pi n over a cosh y. You can see then that we'll have a pi n over a that we can factor out on both. Sinh b minus y cosh y, minus minus is plus. We'll have cosh b minus y sinh y. This results in a sum of angle identity for sinh. So we'll have this pi n over a, and then we'll have the sinh of the sum of these two. But when we add these two angles, the y's cancel, and we just end up with a b here. The only way that can equal 0 is if b is 0, and we'll assume that it's not. So this will not be 0, and we get linear independence. We'll have then that v1 is minus the integral of y2, which is the sinh of pi n over a y, times our function bn of y, divided by the Wronskian, which is pi n over a sinh of pi n b over a all times dy. Note that the Wronskian is constant. v2 will be positive integral y1, which was sinh pi n over a b minus y, bn of y over the same Wronskian. And then we can construct our solutions. But before we do so, I want to recall that these have arbitrary constants that we can add to them, but those only contribute to the homogeneous solution. Alternatively, we can integrate this as a definite integral. For v1, we can integrate from 0 to y. And for v2, we can integrate from b to y. We'll change this variable in here to some other dummy variable when we do that. Say s and s. These are going to be both functions of y. When we're done, our solution is going to look like y1 times v1. Remember, y1 is the sinh of pi n over a b minus y, and we're multiplying by this v1 plus y2, which is sinh of pi n over a y times this v2. Now the salient point. Check out y of 0. If you plug 0 in here to y1, you don't necessarily get 0, but if you plug it into v1, you do get 0. And similarly, if you plug in 0 here on y2, you get 0. So it satisfies the left boundary condition. What about the right boundary condition? If we evaluate the y1 at b, we get 0, because hyperbolic sine of 0 is 0. Not true for y2, but if you take a look at v2 and evaluate at b, you also get 0. So we satisfy both of the boundary conditions, which is very nice. We're very happy about that, and we're able to proceed and construct our solution to Poisson's equations from here. This completes the way in which we would construct these for these a n of y's. We'd sum these then. An advantage is the increased speed of convergence of the solutions in this new method. We're going to reprise the equation, the Laplacian of u equals 1, where u, evaluated on the boundary of the unit rectangle, is 0. Well, first, represent f, which is 1. To do that, we'll take Bn of y to be twice the integral from 0 to 1 of 1 times the sine of pi n x. It's easy to see what you get here. You get negative 2 over pi n. Well, the cosine of pi n is negative 1 to the n, and the cosine of 0 is 1. Note, Bn of y is identically 0 if n is even. And it's, let's see, if n is odd, we have negative 4 over pi n for odd values of n. With our basis, y1 is the hyperbolic sine of pi n 1 minus y, and y2 is the hyperbolic sine of pi n y. The Wronskian is pi n times the hyperbolic sine of pi n. Recall that our differential equation was a n double prime of y minus pi n squared a n of y equals b n of y. Well, for n even, the bn's are 0, and so we just have this homogeneous solution. So for n even, then we can get something non-trivial. We'll have a n of y to be minus sinh pi n y, the integral from 0 to 1, sinh pi n 1 minus y, and we have to multiply by the bn when we're integrating, but that just gives us a constant, which is minus 4 over pi n. We also divide by the Wronskian, which gives us another factor of pi n, and then in the denominator we get a hyperbolic sine of pi n. Fairly simple. And then the other term. Plus, we'll have the same as before. We'll have a negative this time, 4 over pi n squared, hyperbolic sine of pi n. The numerator will have a hyperbolic sine of pi n times 1 minus y. We'll integrate from 1 to y, hyperbolic sine of pi n y. And we should be using dummy variables in these locations here. On the first term, when we integrate, because of the negative coefficient on s, we'll get a minus. We'll also have another factor of pi n in the denominator. We can factor the negative 4 over pi n cubed. We'll have a hyperbolic sine of pi n. Now what's left over? We'll have this sinh pi n y. When we integrate sinh, we get cosh. We've already taken care of the minus pi n in the denominator. We're evaluating if this is s from 0 to y. And then plus, because we factored out the negative, sinh pi n 1 minus y, and we'll have cosh pi n s, but we're evaluating from 1 to y in this case. This gives us then negative 4 over pi n cubed sinh pi n When we plug in y, it is what it is. We'll have sinh pi n y, and then cosh pi n 1 minus y. When we plug in 0, we'll have minus cosh pi n. The evaluation's only applying on these last factors. And then on the next term, plus sinh pi n 1 minus y, we'll have cosh pi n y minus cosh pi n. These are the an of y's. We multiply these onto our basis functions, sine of pi nx, and add those up for even values of n as n goes from 2 to infinity. I'd like to show that for the heat equation, U cannot attain its maximum on the interior of our region. You'll recall that our region is described by 0 to L and then 0 to T. The boundary of that region is just these segments here from 0 to L and from 0 to T. So the boundary consists of this side, t equals 0, x equals L, x equals 0, and t equals capital T. But what is more, we want to show that on this boundary, the maximum cannot occur here either. We've already shown with our lemma that at a local maximum, the function u satisfies, we have a concavity condition, it's concave down, or the second derivative could be equal to 0. If we could show that at this local maximum you get a strict inequality, then let's think about the consequences of that. If that's true, we already know that at the critical point, the time derivative would be greater than or equal to 0, at least if it's on the interior, at least as you go up towards it, so that we have a max at that point. And if it's at the end point, it has to go up as it goes towards that. We can think of ourselves as having the rectangle here, the temperature distribution as being like a surface over the top. If you have a local max, if let's say this is x and t, then as time increases towards that maximum, you have to have the function increasing, which means a positive derivative. Of course, at the critical point, it should have a derivative that's equal to 0. Same thing if the maximum occurs as you tend towards the endpoint, the function should be going up as you end up at time with a maximum at time big T. If this is true and this is true, then it's not possible for U to be a solution to the heat equation. To see that, if Uxx at the critical point satisfies the heat equation, we have 1 over c squared ut, x naught t naught. Well, if that's bigger than or equal to 0, there's no way that u can be negative. And that reaches a contradiction. Therefore, the maximum can't be of the form a strict inequality like this at any interior point to the region, but not even at t equals big T. If it happens there, you still would have to have, if the second derivative with respect to x were strictly negative, you'd still have to have this contradiction arise. That implies that the only place that you can have this critical point is somewhere along this boundary. However, the problem that we have is that we don't have a strict inequality. We have a conditional inequality. And that means we're going to have to work a little harder to get this result, where the maximum occurs at one of these boundaries, not at the boundary with little t equal to big T. There's a device that we can use that will get us around this problem. We're going to set v equal to u plus x squared divided by n. This will allow us to take the limit as n goes to infinity to recover this function u. What we should note is that if u is a solution to the heat equation, what that gives us then is Vt. Notice Vt is ut. That's going to be, let's compare that to Vxx. Vxx is uxx plus 2 divided by n. If u solves the heat equation, this is going to be c squared uxx. But uxx is Vxx minus 2 over n. And if n is from the natural numbers, this is going to be strictly less than c squared Vxx. So Vt is going to be strictly less than c squared uxx. So I want to prove the following lemma. We're going to let u solve the heat equation on our rectangle. Where we're assuming that the data on x equals 0, x equals L, and t equals 0 are bounded by some maximum value, capital M. UR, UL, and U naught are bounded by some M. Just as before, we're going to set V to be U plus x squared divided by n. Then Vt is strictly less than c squared Vxx, as we've already seen. Also, the maximum of this function v does not occur in the interior or at little t equal to big T. It occurs on the boundary x equals 0, x equals L, or t equals 0. And finally, for all x and t within our region, v will be bounded by the maximum of the data on the boundary plus L squared divided by n. We've already seen that 1 is true, so we have only to prove 2 and 3. By way of contradiction, if v attains a local max at an interior point or at t equals t at some point x naught t naught, by the previous lemma, we have Vt at this point is bigger than or equal to 0, and Vxx at this point to be less than or equal to 0. But by the first part, this Vxx at x naught t naught must be strictly greater than 1 over c squared vt at x naught t naught, where this is supposed to be non-positive and this is supposed to be non-negative. You can't have this inequality. This is a contradiction, which means that the maximum cannot occur at any interior point, or even where little t equals big T. So now we need to prove this last part. To do that, remember that v of xt is u of xt plus x squared over n. Now, the max occurs on the boundary. So for any xt on x equals 0, x equals L, or t equals t, we have v of xt is less than or equal to m, and the biggest the last term can get on this interval is L squared over n. And we're done. To finish the proof for the maximum principle, for the heat equation, we just note that if U is a solution, then set V equal to U plus x squared over n. By our lemma, U is equal to V minus x squared over n, which is less than or equal to V, which by the lemma is less than or equal to m plus L squared over n. Now all we have to do is take the limit as n goes to infinity to obtain the bound on U. The maximum had to occur at the boundary, and all throughout the boundary, U is bounded by m. And what is more, the maximum is achieved at the boundary. So we've completed a look at the maximum principle for the heat equation. Let's complete the analysis for Laplace's equation. And again, we're assuming that we have a suitable maximum on the boundary. Similar to our analysis before, we only need to look at the maximum. The minimum will follow in a similar fashion. Here, we're assuming that our region looks like this. So that x is between 0 and a, y is between 0 and b. The boundary of the region will be at x equals 0, x equals a, y equals 0, and y equals b. So in our proof, for any local max on the interior of the region, we'll denote the interior as with a superscript of a circle, because at interior points you can always draw a little circle around them that lies entirely within the region. A solid disk around each point, open disk. If we have two orders of differentiability, it's 2 times continuously differentiable, then we must have the concavity in each direction to be less than or equal to 0. Again, if one inequality were a strict inequality instead of one of these conditional inequalities, then we would have uxx plus uyy is strictly less than 0 at the point x naught, y naught. And we're using y naughts here. And that would be a contradiction. So again, we have a problem with these kinds of extrema occurring on interior points, but we don't have to have strict inequalities in order to have extrema, even in interior points. So we need a similar device to what we had in the heat equation. So here's what we do. We set v equal to u plus x squared plus y squared over n. Consequently, vxx plus vyy will be uxx plus uyy, which is 0 because u is a solution. But we're also going to get 2 over n plus 2 over n, which adds to 4 over n, and that's strictly greater than 0. It follows that v cannot have a local max on the interior of our region. And that implies that the local extrema occur on the boundary of the region, one of those little elements of the boundary. Well, on the boundary, we already know the function u is bounded by m. So let's look at this. uxy evaluated at xy on the boundary of the region, it's going to be equal to v minus this stuff, which is less than or equal to v. And because u is no bigger than m, x is no bigger than a, y is no bigger than b, we're going to have this be less than or equal to m plus a squared plus b squared over n. So if u attains this max on the boundary, and on the boundary u is going to be bounded by this expression, we take the limit, we'll send n to infinity, and we'll have u be no bigger than m. And that completes the proof. We have only one more section to cover in this module, and that covers some delicate issues in analysis that we skipped over earlier so that we could get as quickly as possible to the meat of the subject. After this module, we'll consider next the heat equation, wave equation, and Laplace's equation, etc., Helmholtz equation, in other coordinate systems beyond rectangular coordinates. As you'll see, this leads to some very interesting analysis.